So my weight in the metric system would be 72.6 kilograms times 9.81 meters per second squared equals roughly 712 newtons. Okay? That's my weight in metric units.
Correct.
So, over here, we have the equation due to gravity. Okay. And that says that the force of gravity is equal to the gravitational constant times the mass of one object, in this case, me, this is represented by a little m, times the mass of another object, which would be the Earth, divided by the distance between them squared, which in this case would be the radius of the Earth. Now you should actually add the distance to my center of mass from the Earth's surface, but it's so insignificant that it doesn't really matter. Okay? And the gravitational constant, which I should have written down here. So if you plug the mass of Earth, which I have written here, which is 5.9726 times 10 to the 24th kilograms, really big number. My mass, 72.6 kilograms, and the gravitational constant, and the radius of Earth, which is 6,371,000 meters, you will get 712 newtons, roughly. Pretty close. Close enough to say it's the same. To say that to accept the fact that, well, the assumed fact that gravity is causing this weight, and that's why I have weight is equal to the force of gravity on here. Okay, this is what is taught in physics.
Okay, so basically Brian has gone through the equation to calculate his weight in newtons using weight equals mass times the acceleration of gravity, and then he has compared it to the universal law of gravity, which is gravity equals the gravitational constant times mass 1 times mass 2 over the radius squared. And he's put in the numbers and he's come up with the same number of 712 newtons as the weight equals mass times gravity equation. Now, there's a couple of things that I think you ought to notice here. First of all, he made a big point that they were quote-unquote large numbers when you're dealing with the radius of the Earth and the mass of the Earth. Well, yeah, they are large numbers. The Earth is very large. But the fact that they are large numbers should not intimidate an engineer or a scientist. Second of all, he started talking about the fact of gravity and then caught himself. The claimed theory of gravity, or whatever euphemism he used, to try and somehow subtly invalidate this whole concept and show that it was quote-unquote still in question. And that is his flat earth narrative. So he's going to go on to discuss the gravitational constant and how it's basically a made-up number done for convenience rather than any relationship to reality. But before he does that, let's just go ahead and go over the gravitational equations and how they were derived and where we got the gravitational constant from. And we're going to touch on the Cavendish experiment as well. So let's cue up the music and then we're going to get started.
This force of gravity actually creates my weight, but there's just two different ways we can calculate it. Okay. But Newton came up with this before he came up with the equation for gravity. And in fact, Newton only proposed the equation. He didn't actually finish it. He said, from looking at the solar system model and watching things in the sky that he thought, or he assumed, were orbiting Earth based on Copernicus' work, that the force of gravity was proportional to the mass of one object times the mass of another object divided by the distance between them squared. Okay? He said they're proportional, they're not equal. So what this means is, if either one of these masses go up, or both of them go up, the force of gravity also goes up. But as the distance between them increases, the force of gravity goes down. And as you can see, this is square, so distance plays a big part here. So he eventually proposed that he needed this big G up here, this gravitational constant. And he didn't know how to determine that, but he did know that the units would be what we have right here, meters cubed over kilograms times second. Now, he might not have been using the metric system then. I haven't actually looked into that, but he would have been using something similar. So I'm just going to assume that he used metric units, because if you combine the units in this proportion right here, you would get, assuming the masses are measured in kilograms, you would get kilograms squared over meters squared. And if you multiply that times this factor down here, you will end up with kilograms times meters a second squared, which is equal to a newton, or a unit of force. Okay, just like I showed in the original equation, the original bread and butter equation over here.
Okay, so let's go ahead and bring out the whiteboard and see if we can make some sense of all of this. Now, what he is saying is that after Newton, mass times gravity, which is weight, right, is proportionate to mass 1, Brian's weight, mass 2, the weight of the Earth, over the distance between the two, the radius, squared. Now, let's have a look and consider what proportionate means. Now, we can actually measure this number right here. We can put Brian on a beam balance and compare him to kilogram weights and figure out how many kilograms he comes up with. We can actually measure the acceleration of gravity. Now, so those are known numbers. So we also know Brian's number over here. This is his mass. And we know the radius of the Earth. So the question becomes, what is the mass of the Earth? Now, let's look at what a proportion means. Now, a proportion means, let's go ahead and we'll make this a little bit smaller. But what a proportion means is that this number right here, a known number, is related to these terms. These are the nuts and bolts terms over here. So if you want to get right down to it, you change these as the independent variable, you end up with a change in the dependent variable. But in order to make this side of the equation over here actually equal something over here, we have to multiply it by some sort of a constant. Now, there's another term in there that's unknown, but it seems to not have any relationship to these terms over here, the mass 1, the mass 2, and the distance that are the variables. We just vary those variables, then multiply it by a constant, and we come up with our answer over on the right side. So what would this constant be? Let's go ahead and move it around a little bit and see what we can find. So here's our original. We're just going to call it K for the moment. Mass 1, mass 2, distance squared. So what we'd like to do perhaps is isolate what that is. So what we're going to do is we're going to leave mass times gravity on this side of the equation. We're going to divide that by mass, these are both mass 1 by the way, times mass 2, and then we have to bring d squared, sorry I forgot the square there, but d squared up here, And that will actually equal our constant. Sound good so far? So let's go ahead and figure out what these are. First, these two right here cancel out because they're both mass 1. So it becomes gravity times distance squared over m2 squared. Now, or excuse me, over m2. So what our units are going to be is g is in meters over seconds squared. D is in meters and it's squared. And down here we have kilograms. So we end up with meters cubed over seconds squared times kilograms. So whatever these numbers work out to be, those are the units that we're going to have for K. Okay, so now we're cooking with gas. We know that the weight in newtons equals this constant, which we're going to call big G, the gravitational constant, times mass 1 times mass 2 divided by the radius squared. Now, what do we know in that equation for, say, Brian's weight of 712 newtons? Brian's mass is 72 kilograms. We don't know the mass of the Earth. We don't know the gravitational constant, but we do know the radius of the Earth. Can we perhaps design an experiment where we can control all of those variables and maybe calculate what the value of G, the gravitational constant, actually is? Well, as it turns out, we can. Let's have a look. Okay, so here we go. Now we're going to do some science stuff. Let's say that we have two masses. We have a large mass and we have a small mass. Now, mass attracts mass. So what's going to happen is that these two masses are going to attract each other. And we know that if we apply another force out here in that direction, to the point that this object right here is in balance between this force and that force, we can measure what the attraction there is. Okay? Now, here's a problem that we're going to run into. We are on Earth, and everything that is on Earth is subject to a gravitational acceleration downward simply due to the Earth. How do we isolate this system to just measure that force right there? Well, let's go ahead and have a look at something. Now, this is the reading from an accelerometer in my iPad, and you're seeing it in real time. As you can see, let me just tap the table a couple times. You can see that that actually occurs right as I do it. Now, we've got a couple of things here. First of all, on top is a white line, and that is measuring the entire amount of gravitational acceleration that is acting on the iPad. And as you can see, it's approximately, total g-force is 1g. Now, down at the bottom is the blue line. Notice that if you look over in the upper right corner, you'll see the Z or Z-axis is measuring 1g. So all of the force on my iPad right now is acting in the Z-axis, which is the front to back axis on my iPad. It is not acting up and down along the long edge, nor is it acting along the short edge. So we'll have a quick look and I'll show you exactly how this is set up. And there you can see the actual setup on my desk. There's my iPad, and you see the readings that we had just a moment ago. And you see that the entire force of gravity is directed from the front of the iPad to the bottom in the Z or the Z axis. The short axis of the side of the iPad is the x-axis. The long axis is the y. Okay, so let's have a look and see how we can do this experiment. If we set the balls one on top of the other, like so, we are in line with the force of gravity going down in the z-axis. However, if we set them side by side, we are working in the x-axis, or side by side this way, we are working in the y-axis, and as you can see, the gravity effect in both of those axes, I got yelled at for that the other day. The gravity in both the x and the y-axis is zero. All of the force of gravity is directed to the z or z-axis, which is that axis right there. Now, if we do stack them up this way, we are going to have the effect of the Earth's gravity, but like that or like that, we will negate the effect of the Earth's gravity field. Okay, so let's have a look at how Cavendish's experiment was actually set up. And this is a modern version of it. But basically what you have is right in the center, you see an inverted T that has two small gold balls on it. These are the small balls. And the thing that it's hanging from is the torsion scale. You see that there's a mirror, like a dental mirror, on that torsion scale, and there's a light source shining on it, reflecting off on a gauge, which is graduated there in the end. Now on the left, you will see the large balls being moved towards the small balls, decreasing the radius and increasing the gravitational attraction between them. Now watch what happens when they come together. You see how the balls are brought in and cause a deviation of the light. You also notice too that these balls are perpendicular, in a plane perpendicular to the plane of the acceleration of gravity. So these will be in the x or the y axis. Well, now the magic begins. We know the force of attraction between both of those metal balls in the Cavendish experiment. We can measure that directly with a torsion balance. We know the mass of ball number 1, and we know the mass of the larger ball number 2. We know the distance between them. What we don't know is our elusive gravitational constant. But if we move these around a little bit and make the force in gravity times distance squared over mass 1 times mass 2, we know that we now have a value for G. And that, my friends, is how we found the value for G. Now, let's check the units again, shall we? So here we go. Recall that G equals the force of gravity times the distance squared over mass 1, mass 2. So let's have a look and see what we have here. Okay, so first of all, the force is in kilograms per meters second squared. That's what a Newton is. Okay? Now, D2 is in meters, or D squared is in meters squared. Mass 1 and mass 2 are both in kilograms. So this kilogram will cancel out. This meter will combine with the meters squared and will give us meters to the third. We have second squared times kilograms. And that is our unit of measurement for the gravitational constant. Things worked out right. Well, now that we've figured out what G was using small masses, let's do something a little more ambitious. Brian's weight was 712 newtons. Okay. His mass was 72 something kilograms. We don't know the mass of the Earth, but we do know the radius of the Earth. So, and then now we know big G. So, we know that term, we know that term, we know that term, and we know that term. Let's weigh the Earth. Let's find out what the mass of the Earth is. And the way that we would do that is simply rearrange the equation. So, we have force of gravity equals big G times mass 1, mass Earth, over the radius of the Earth, squared. So, we're going to have the force of gravity times the radius of the Earth squared, divided by mass 1 times G equals mass Earth. Pretty easy, right? That's straight to there. Well, here, we'll do this another color so it's a little easier. That's straight to there. This is brought over. This is also brought over down to here. And then G is brought over to the other side of the equation as well, and all that's left is the mass of the Earth, and there it is. We just calculated it. And that's how we found the mass of the Earth. And then, by taking the known circumference of the Earth and finding the volume of a sphere with that circumference, we were able to calculate the density of the Earth. And we found out something really cool with that. The density of the Earth on average was closer to that of iron than it was to stone. And that was the first hint that the Earth had an iron core. Guys, we just weighed the Earth. We figured out the mass of the Earth. We figured out the gravitational constant. And we now understand how the Cavendish experiment was performed. And that's pretty cool. Science is just so freaking awesome. Well, even though that was just a joyous experience to do that, tomorrow we're back to work with our friend, the flat earth engineer, Brian Mullen. And we're going to see how badly he screws all of this up. But in the meantime, this is Bob the Science Guy, and I'm signing out from Northern Michigan. I've had enough for tonight. I'm going home. Take care, guys.
This rabbit hole's too deep for me. Feel my brain getting real sore. Bob, this side.